This visual of a fracturing geometric block autonomously rearranging itself mirrors a transition in how we use software. For years, we've used prompts to generate text. Now we are handing those same models the ability to execute the steps they describe. Up until now, our chatbots have acted largely as advisors. You can ask a model a complex question, and it will generate a highly intelligent response, but that response sits isolated on a screen. The system has no way to act on the advice it just gave you. This leaves you with the actual labor. You are the one gathering context, switching between browser tabs, and copying information from your Gmail into a chat window to keep the conversation going. If you ask a model to schedule a meeting, it will write out a perfect step-by-step guide on how to do it, but it lacks the physical access to open your calendar, check your own availability, and send the actual invite. That gap between knowing the answer and doing the work is closing. By connecting language models directly to external tools, developers are building AI agents capable of autonomous action. Conversational AI helped us think, but it left the heavy lifting to us. We ended up with highly optimized instructions, yet we still had to manually perform every single click and keystroke ourselves just to get the job done. To close that gap, developers created AI agents. An agent combines the reasoning engine of a large language model with direct access to digital tools, allowing the software to function as an autonomous digital employee. This animated flowchart shows exactly how that autonomy works. It represents the react pattern, which replaces the old single prompt and response interaction with a continuous thinking cycle: reason, act, and observe. In the reason phase, the agent receives a task and independently evaluates it. It pulls in external context, like system instructions and conversational memory, to figure out exactly what the user is asking for. Moving to the act phase, the model determines if it lacks the information needed to solve the problem. If so, it reaches out to use a tool, like running a terminal command, searching the web, or reading a local file. Finally, in the observe phase, the agent takes the new data it just retrieved from that tool and feeds it back into its own memory. It looks at the result and decides what its next logical step should be. This continuous loop removes the requirement for human intervention between every step. The machine iterates on its own logic, testing and observing until the task is completely finished. To see how this architecture gets deployed in the real world, we can look at an open-source project called OpenClaw. You can install it locally on your laptop or a virtual machine to act as a personal assistant. This animated diagram breaks down OpenClaw's structure, starting with a central hub called the gateway. The gateway is a control plane that handles session management and routes messages to multiple agents running simultaneously. Notice how the incoming data lines change as they pass through these filters. Those filters represent adapters. They capture unorganized requests from external platforms like Slack, iMessage, or Microsoft Teams, and translate them into one unified format for the gateway to process. From there, the formatted request moves down to the execution layer. This is where the underlying language model is given hands. It gains the actual capability to manipulate a web browser, execute specific terminal commands, and control enterprise applications directly. By standardizing the way humans communicate with the model and granting it direct access to system tools, the OpenClaw architecture physically wires a language model into your digital environment. There is a hardware limit to how much access you can grant at once. If developers try to feed a language model the rules and instructions for every single tool on your computer simultaneously, it will instantly overload the model's context window and crash the system. OpenClaw solves this capacity limit using skills. Skills are individual markdown files that contain specific workflows. Instead of loading everything up front, the system injects brief metadata about these skills into the agent's memory, allowing the model to read the full file only on demand when a specific task requires it. This modular approach allows the agent to handle highly complex workflows. It can autonomously edit your Trello boards, schedule appointments on your Google Calendar, or even build and test Docker containers without human input. But granting software total autonomy to execute code on your local machine creates a severe set of vulnerabilities. Building an AI with perfect memory and a vast library of executable skills creates an incredibly capable assistant. But if left unprotected, it also creates an unmonitored backdoor directly into your hardware. Because an agent like OpenClaw runs entirely locally, it holds direct access to your file system and terminal. A single misconfigured environment variable or a malicious skill file can allow external actors to run destructive commands natively on your computer. This diagram illustrates a vulnerability known as prompt injection. If an agent scans an untrusted email, hidden malicious instructions embedded in the text can be processed as legitimate commands. As it enters your system, the agent executes the hostile code, hijacking its own agentic loop. Security protocols are racing to catch up as this architecture spreads. OpenClaw is just one high-profile open-source project among dozens of rising frameworks like LangGraph that use these autonomous loops to drive action. We're moving into a dynamic where the AI model takes over the role of the orchestrator. As the system plans, executes, and observes its own actions, human users are stepping back from the manual labor and into the role of high-level supervisors. As you can see in this flawlessly synchronized mechanical system, the role of AI has moved into active orchestration. The model completes the work while the human supervisor defines the objective. If you want to stay updated on how these autonomous systems are developing, be sure to like this video and subscribe for more.